Good afternoon, fellow foundrymen. This is Sendil Kumar, Secretary from IIF Chennai chapter. Before we get to things started, I am once again requesting all the members to switch off their mic, and also you can also put your camera on off condition. It gives me immense pleasure in interacting with you for yet another webinar, which is being conducted by IIF Chennai chapter, and especially for our non-ferrous series. And what is special today's seminar? If you ask me that question, I would say speaker. That is our Prabakaran sir. And we had a very great opportunity to work with him for our last Aluminum Conclave 2023, which has happened in April. Last April, we completed. It was a very successful event. I really admired for his excellent presentation skill, which is very simple and neat, and his personal care for each and everyone who is surrounded by him. To get things started, now I request our chapter Vice Chairman, Mr. Vignesh Ramanan, to welcome the gathering, please.
Thank you, Sundar sir. Very good afternoon, fellow foundrymen. It gives me immense pleasure in welcoming you all to this technical webinar conducted by IIF Chennai chapter. This is our 8th program for the day, for the year. That is since the year has started in May, and this is our 3rd aluminum program for the year. Understanding that aluminum is the future metal, and due to norms of lightweighting and many more opportunities, aluminum is what that has to take the center stage coming years. Keeping that in mind, Chennai chapter has at least committed to conducting at least one webinar on aluminum every month, and this is being done month on month. More on today's topic and our speaker. Like Cyril sir said, we had an amazing opportunity to work with Prabakaran sir during our 13th edition of the Aluminum Conclave, and he's a master in die tool making, and he talks with conviction, and I would say he's an authority to talk about today's topic. So keeping that in mind, we are so fortunate to have amidst us a legend from the aluminum industry. Let's put on our thinking hats and grasp what he has to say. Thank you.
Thank you, Vice Chairman. Our today's speaker do not require any introduction. I think he is a very well-known figure in non-ferrous industries. Only as a customary, we need to introduce. To introduce the speaker, I request now Mr. A. Siddharth, our council member, to introduce the speaker to him to the audience, please.
Thank you, sir. So as Sendil sir and Vignesh mentioned, we have seen his energy and commitment to anything he takes up. I had an opportunity to work with him directly for Aluminum Conclave. Just to see the amount of energy he brings to the forum, I think it was great to learn from one of the legends of non-ferrous industries. And as Sendil sir and Vignesh said, aluminium moving forward is one of the most important. We very happy to have him as a speaker. So just a formal introduction, even though sir needs none in IIF fraternity. Mr. N. Prabakaran graduated mechanical engineering during 1979 at Government College of Engineering, Coimbatore. He got experience from Union Company Motors, Chennai, Isaka Industries, Coimbatore, and Sundaram Clayton Limited, Chennai. He played a major role in introducing and implementing new processes like SMED in pressure die casting. He founded Dietech India Pvt Ltd in the year 1995, and Dietech is one of the well-known industries in Chennai and throughout India actually. Engineering excellence with innovative thinking, systems and later technology is his motto. He believes in systems and teamwork, foundation for an organization. Under his leadership, Dietech evolved many techniques in manufacturing die casting dies with high technique equipments. Cell concept was introduced by him to give more attention to the requirements of the customer by the manufacturing team. He has 40 years of experience in die casting field and has established a modernized tool room at Sri Perambatoor in the year 2011 with 300 employees in 1.6 acres of space. I have had an opportunity to even visit his plant on the detailing he has gone in towards the systems and process. So it's not just talk, he has actually implemented it. And Dietech India is a leading tool maker for high pressure die casting, low pressure and gravity die casting. Dietech is capable of manufacturing HPDC dies ranging from 250 tons to 2,200 tons, gravity dies for castings up to 20 kgs. Our major customers are TVSM, Maruti, Honda, Yamaha, SEL, Bosch, Wapco, Sunbeam, and Regal Beloit. He is not only a successful businessman but also a noted speaker on gating techniques, cooling systems in die, latest techniques about die manufacturing at various presentations in Alucas, Tagma, IIF, and ILZDA. His objective of providing extensive support to customer resulted in development of customer portal web application to review the progress of dies online. For easy, quick, and error-free die design, he founded Auto Mold Base, which is an online design software going to be released very soon. It is my immense pleasure to have you on board, sir. The stage is yours. Please enrich us with your knowledge.
Thank you, Siddharth. Thank you very much.
Prabakaran sir, floor is yours. You can start your presentation.
Yeah, please. Good afternoon to everybody who is attending this seminar. Probably I am going to touch the PQ square diagram concept. But at the same time, a lot of equations are going to come. So I am not going to teach these equations, rather than I am going to give only the concept. In turn, I will finally conclude how we can make this facility in your company. Are you able to hear all the people?
Yes, sir. Yes, sir. We are able to hear you.
Yes, sir. Perfectly audible, sir.
Now, probably if you are selecting a casting to be for a pressure die casting, probably we have got only the casting in your hand, knowing the weight and normally what is the tonnage. The machine selection has to be first made. But this is not nowhere related to PQ square, but we will have to know machine selection is very important for the PQ square. That way I am going to explain a little about that machine selection. That is what we call as a tonnage calculation. So normally people, there is a 3 dimension for any casting, XY and Z. In a parting line, normally the XY will be there and Z will be coming into the depth of the cavity normally in FD and MD. The projected area is called in XY directions. That XY area, now this component is called in green color, it was shown, that is a projected area. And the next is orange color is a biscuit area. And the runner is in yellow color, and the blue is in overflow area, and the children is also there. But at the beginning, we don't have all this, the runner systems and the overflow. So there is one more method I'm going to tell. Before going that, I'll do that. Yes, okay. If the runner system projected area is not available, consider that 40% of casting projected area is a runner systems area. If we are going to consider that, how to calculate the tonnage for a particular castings? Normally, very simple, what I can say that it is a projected area into the specific injection pressure. Please note that what I am mentioning is a specific injection or casting pressure. So probably I will explain why I am very specific on this. When I am doing the PQ square diagram, I will explain that. So we should know about the projected area into specific injection pressure and the factor of safety. Probably the factor of safety may vary according to the people. Suppose if we want, normally 20% is minimum requirement. Suppose the people think of that we don't want even a little flash, even a thin flash is not requirement, will not come into account, then we can go for higher tonnage to avoid the even minimum flash due to die gap and as well as the metal temperature variations. Okay, apart from that, there is one more thing. Suppose the component is very plain without any core. There is not a big problem for us. But suppose if it is going to have a core, how we have to calculate that projected area from the core? That I will give you one guideline. Suppose if it is going to be a mechanical core, the projected area of the core into tan 21 will be your tonnage. That is a projected area, effective area to be added in the projected area of the casting. Suppose if it is in a hydraulic core, then you can know that the tan phi degree has to be multiplied and then taken. This will be taken into account of the projected area of the casting. So please, tan 21 will be a bigger value, tan phi will be a lesser value. So this you keep in mind. Suppose if you are going by higher tonnage, to reduce the tonnage very minimum, suppose we want to go for a 400, I want to do it in 350. So suppose I'm having a factor of safety only 10%. I want to improve another 10%. So what we can do, we can go for hydraulic core so that your projected area will get down. In turn, the tonnage requirement also will get down. So this is an advantage will be there in hydraulic core and mechanical apart from. But more than that, in hydraulic core, we'll have a cylinders and attachment to the machine. These are all the real problem always in the shop floor. But try to use the support. Suppose if at all you're having any problem in having a near tonnage, some compensation if you need it, we can think of hydraulic core also. Apart from that, I told the specific injection pressure. Normally we can think of any commercial casting, the specific injection pressure can be assumed for 300 to 500. And technically, what I am saying that commercial means is a decorative component, we can say. Second is a engineering component. Normally it is going to be a bracket, and then these are all coming under 500 to 700. If it is going to be a pressure type, suppose we are going to do the leak test of the component by air or by water or something, then we will have to think of the 700 to 1000. This selection is more important to have the right tonnage of the machine. Suppose the component which is, if you are not considering, say you can say it's a decorative component, you can have a lesser pressure. In case of a pressure type component, it will be almost doubled. You can see 300 to 700, there is a 500 to 1000. So as per the component requirement, we'll have to select the specific injection pressure. In turn, we'll have to select the tonnage. And then one more. With this, I am going to stop. In any clarifications required in this junction? Anything you want to clarify? You can put a question in front of us so that I will try to.
Gentlemen, you can put it in the chat box or you can unmute yourself and ask. This can be interactive.
I hope that people will be more familiar with these calculations. Now we will go for a conventional gating system concept. In a conventional gating system, what you adapted earlier, now what are all the machine elements are considered in that? That is what I am putting in the picture. Probably what we are thinking that we will have always a cavity fill time is a 40 milliseconds as a standard. And we will think of the gate velocity also 40 millimeters. These are all the assumptions will be made. From there, we will try to find out the gate area by taking the volume of the component. Next slide, it will come how we can make it. But in this picture, what I want to convey to you, the injection force in a conventional gate system, we are not at all, we are thinking that this machine will be capable of producing what we are making the gate area. So we do not know, only by machine tonnage, we know what is the component which is coming into the line. As per the sketch, what I want to convey to you, in the previous conventional gating systems, the injection force, we are not at all knowing, but at the same time, we are thinking that it will produce from the machine. This is a big gap between peak square and as well as the conventional gating system. How to come out of the normally, how we can make it a gate area? Everybody knows that what the weight of the component, from the weight of the component, add the overflow weight. And if you want, you can add the chill path weight also, and then come to the volume. We will have to find out weight by density. From the weight by density, we will find out the that is a discharge rate, that is a fill rate. Fill rate is nothing but a volume to fill divided by fill time. Fill time, as I told already, in a conventional, we are thinking only 40 milliseconds, and gate velocity is 40 meters per second. From there, we can find out the gate area by fill rate divided by velocity of the gate. What we are thinking 40 meters per second. From there, we can find out the gate area required for that component. With all these standard calculations, one thumb rule what we are trying to be found out, the gate area in square mm, always the weight of the casting of in grams divided by 4 is equal to square mm. This is this is only some thumb for what we are adapting. By seeing the component, how much will be the gate area? Suppose if it is in 200 grams, then 200 grams divided by 50 mm square is the requirement of the gate. This is a rough thumb what we can have in our mind. So this also can be used. These are all methods that we followed in the earlier stage before coming to peak square diagram. And one more thing, probably at the stage itself, we know what is the fill time according to wall thickness, according to weight of the component, the fill time will get changed. Suppose if we are having a 3 mm wall thickness of average inside the casting, then we will standardize at 40 milliseconds. If it is less than 3 mm, then we will go for a more fill time, say 40 and above, that is 45 or 50.
Sir, you are muted, sir.
Sir, Prabakaran sir, you are muted.
Are you able to hear?
Yes, sir.
Now it's okay.
What has happened? Okay. So, as with this fill time and gate velocity, we have got according to wall thickness and as well as intricacies of the component we used to select in the previous stage. These are all now in PQ circuit. These are all we get to overcome. Anyway, we'll go through that and then we'll come back. So normally what we are getting in the die casting machine, it is not a PQ square. What we are getting is only a V1, V2 and as well as the third phase of time and as well as the pressure. This is what we are getting the map usually from the machine. Why I am putting that, this is not really a PQ square diagram, it is a output of the machine, especially the plunger velocity and as well as the specific injection pressure, what it is happening inside, that is what it is giving. Now, with this stage, I want to interact with the people. Anybody wants any clarification in this? Any questions? Okay, then we can go further.
Members, please feel free to unmute yourself and ask questions, or if not, you can type it in the chat and I'll be happy to read it for you guys.
So what is in PQ diagram? What are all the machine elements are involved in calculation? That is what now I am putting inside. But one thing, a big understanding, probably people knows. However, I am going to highlight it. There will be a multiplier is there, which I put it in the dotted line in the sketch. Always in the machine. Normally in die casting machine, multiplier will be there. That is acting as a third phase, but which will not come into picture of PQ square diagram. Will not be accounted in PQ square diagram. It is only added advantage on the pressure die casting to fuse the more material inside or strengthen the material inside the casting. Now, what is happening now in PQ diagram? We are considering a piston area. That is piston area, hydraulic pressure inside the piston area, and we are thinking of dry shot velocity. Dry shot velocity is nothing but a no material. Plunger is very free. At that time, what is the maximum velocity that machine can create? Probably we will try to find out if we are having an attachment on the machine of a sensor having a velocity sensor, or otherwise the machine supplier will try to feed this data. Dry shot velocity, probably the supplier will give the data for us to calculate the PQ square diagram for the purpose of PQ square diagram. And then what we call as a plunger area and the plunger pressure, plunger front pressure maximum. So that is what we call as a pressure in front of the plunger. Okay, these are all the elements which we are considering in the PQ square diagram. Previously, if we could be able to see now, we can see the difference also from the previous. Here only 3 elements are, only one element, if I am not having the gate area only we are taking into account. All other things are not accounted. It's only one element of system is taking into account for the conventional gating system. In case of a PQ square diagram, we are taking a dry shot velocity, hydraulic pressure, piston area, and then front pressure, and actually we are calculating, and then plunger area we are calculating. Now, how to draw a PQ square diagram? There is a 5 steps has been given. Develop a machine power line, develop minimum flow rate line, develop maximum velocity pressure line, develop minimum velocity pressure line, select a die characteristics gate area line. Now we will go one by one, how to draw the PQ square diagram. Now, before going into that, we should understand what it is happening in a pump. Suppose we are having a pump. So how we can maximize the pressure and minimum overflow. Here at this end, we can say this area is going to be a maximum pressure since we are almost closing the valve maximum, but the pressure will be more. Here it is almost flow will be more, pressure will be less. In between, pressure and flow will be equal almost, but depends upon the curve what we are having it. This is only understanding the pressure and the flow characteristics. If you are raising the pressure, flow will get reduced. If you are increasing the flow, pressure will get reduced. This concept we will have to understand for the PQ sky diagram. Now, in a PQ sky diagram, normally we will have a P and Q are in square root. That is what I am saying. The P is inversely proportional to 1 by Q square. So it means we have got a P is a linear, Q is a square. So what we used to do that to make a linear of Q square, they are trying to find out a log scale. Q square is there. If you are going into the maximum mathematics, it will go 2 log Q. That is what it will be converted to 2 log Q. So this is called the log scale and the linear scale. So P will be in pressure. LB, that is what they have put in, but you can go over the kg per centimeter. This is going to have a UK unit. It can be converted to kg per centimeter square. Here is a cubic per second or liters per second. Now, how to find out the maximum pressure? That's what I told you. As I earlier told, we will have to find out a maximum pressure. Here is a maximum pressure that pump can make. Not only pump to metal. What I am saying there. Here, what is the maximum flow which we can take? Okay. This calculation we can do in 2 ways. It's nothing but here the hydraulic pressure is going to be applied. Here the metal pressure is going to be made through plunger to metal. So nothing but area into pressure. Area into pressure is nothing but a force. That is a P1 into A1 equal to P2 into A2. This is nothing but a very simple. This is P2 A2. From there, we are finding out the metal pressure. P, the near plunger, what is the metal pressure? PM. Nothing but hydraulic pressure and this area proportions. D square by hydraulic, D square by plunger angle. From there, we can find out the maximum pressure is created inside the material. Here, what is the maximum pressure is going to happen by applying the 150 bar here. This area will be calculated, this area will be calculated. The ratio between these two areas into this pressure is going to give the maximum pressure here. Metal pressure is going to happen. How to calculate the maximum flow rate? As I told at the beginning, there is a dry shot velocity is taken into account. The dry shot velocity. Dry shot velocity into area of the piston. So that will give the cc per second. The Q is plunger area, square mm, and V is the maximum dry shot velocity. Between these two, we will get the maximum flow rate. Normally, if you are thinking that what we are applying in a plunger velocity will be 2 to 3 meters, probably dry shot velocity will go up to 7 meters per second. This is just a rough estimation what I am giving it. Normally, what we are operating from the 1.5 to 3 meters per second. But in a dry shot velocity, almost it will be doubled. You can take a rough calculation what I am saying. It will be twice what we are using in the machine. That will be the normally dry shot velocity for rough estimation. Now we found out the static pressure and put in that point, and the maximum flow rate we found out that. So you draw a line between these two. This is the first line what we call the machine performance line. The maximum line what you can do, maximum pressure and the maximum flow rate. Now we earlier what I told in conventional, we are only assuming the filling time is 40 milliseconds. And one more variable, according to wall thickness, it can be more or less. This is what the estimation what we used to do that. Here, in case of a PQ square diagram, the fill time is taken into so many factors. Probably what I am saying that T is the casting thickness, and TA is the temperature of molten metal, and TF is the minimum flow temperature of the material. TD is the temperature die cavity surface. S is the percentage of solid fraction, which we are going to touch last. What is the percentage of solid fraction? Probably I'll just put in in front of you now. If the material crosses near the gate, it will not be liquid, it is a slurry. After the gate, the material will be a slurry, it is not a liquid. What it means, the slurry means, there will be some percentage of solid and as well as percentage of fluid. Both will get and form a slurry that will only cross after the gate. So what type of solid fraction is happening? That calculation also, some reference is that will give that. And then these are all the only constant factors. Now I am giving that. Cavity fill time, what are all the elements are involved? As I told you earlier, this is a casting minimum wall thickness. Wall thickness of the casting is taken into account, and the die surface temperature is taken into account, molten metal temperature is taken into account, and the minimum flow temperature is taken into account. This TF will get vary according to material characteristics. Suppose ADC12 will have, suppose some other material, if you are going for a LM24, or otherwise nowadays you call it 6% silicon, 380, 3A, 380 or something like that. So this flow temperature will get vary according to the material grade. And then this is only a solid fraction, which I got only, still we have got only some guideline. As I told you earlier, the fill time is only based on only wall thickness, this and that. Today also the solid fraction is allowable, is still it is only in guideline value is there. Probably nowadays we are also trying to find out from the flow 3D, already they are working and they have given one solution also to find out the what is the solid fraction happening after the gate for a particular component. Probably now the simulation started coming out. Probably whatever you are having the simulation, we can try to find out what is the solid fraction available. Since I am using a flow 3D, recently they were issued and then we are also started working on that. So what I want to convey to you, cavity fill time is calculated through so many factors. It means it has been taken the die surface temperature, metal temperature, and then metal minimum flow temperature, and as well as what I can say, some, okay, that is solid fraction also getting into picture. So probably we are nearing to the accuracy, what I want to convey that. Before conventional from the previous figure, we are trying to approach the very near to the practical factor. Practical, even what I can say, practical gate velocity. We are nearing to the practical gate velocity by calculations. So one more thing, what I told, this is a fill time. Now there is a theoretical discharge. You know the weight of the component. From the weight of the component, then after the gate we'll have to take, suppose you can, if you want, you can add overflow or plus tip path, and then from there we'll have to find out the volume by fill time. Already we calculate the fill time, we know the volume. From there we can find out the theoretical discharge line. This discharge line is going to be put in this. This is a second line. This is what we call it as a maximum fill time line with the required discharge rate. This is what we can find out. So first we have already drawn this line. Now we are going for one more. This is called what we call the vertical line, what we call the theoretical discharge line. This line is calculated and then plotted in the graph. Next, we'll go there. The another interesting thing, what I know, what we, this is normally in a die casting, it is going to be a 40 meter is the mean value. Probably it will go up to 60, or we can go for a 35 or 30. So now what we have taken the standard value of 40 millimeter second and 21 millimeter second. Suppose if we want a thin component, even we can fit it for a 50 millimeter second and 30 meter per second. So this value is your, according to component, we can fix this velocity and then draw a line here. But we don't have any velocity scale here. It is only pressure scale is there, skew scale is there, but we know only, I mean that velocity scale. So how we can convert it, this velocity scale to pressure velocity, what we call as a Bernoulli's equation. You don't much worry about that. The kinetic energy, what we are having here, this is called the kinetic energy. Now we are trying to convert this kinetic energy to pressure energy and for the plotting purposes in the graph. Now this is called what we call as a Bernoulli's equation. Probably only what we know, there's only velocity, and one more I'm going to talk about the coefficient of discharge. This is a density, and then this is a pressure. So this velocity energy is going to be converted to pressure energy. Nothing but a kinetic is going to be converted to potential energy. So here at 2G is a gravity force, so rho is a density. Now there's one more factor, it is coming in the CD. What is CD? CD is what I told you, suppose if I am sending a orifice, a material near the gate, as per the calculation, it will not take place. That will be a efficiency of the discharge, what we call as a coefficient of discharge. Suppose if I think that 10 liters will be transferred to the gate as per the calculation, practically it inside what we call that discharge will not take place from 10 liters per second as per the calculation because of the friction, and as well as what we are not dealing with the liquid, we are dealing with the slurry near the gate. So at that time, this discharge coefficient will come into picture. It is nothing but called the efficiency of the discharge. Now, how to know about the discharge? There is some thumb rule, already some. If it is a liquid, what it is being a liquid. If we are giving a liquid, sending a tube with a tube, direct tube, it will become 9.8. If it is going to be a conversion and then going to be a reduction tube, it's a 9.2, and then straight tube it will be a 7.2. 0.82, this type of 0.8, 0.8. It is because it is a reference to liquid, discharge coefficient of the liquid. Normally for the aluminum and the slurry, what we are taking, even NATCA has recommended directly take a CD is a 0.5. Suppose we could able to find out from the simulation, you can take that value as a CD and then put it in the PQ diagram also. So after calculating, we are already plotting, converting to velocity to pressure energy, minimum and maximum. Now we have one line first we draw here. Another line is a maximum velocity and then minimum velocity. Already we drawn that is a discharge line. So now we have got and one you can able to see one shaded area. This is what the real benefit from the PQ sky diagram. What it means, it is called a shaded window, that is a process window. What we call it as a process window. We have got a flexibility to select any point. Suppose if we are keeping that in center, we have got in a vertical direction, we have got some flexibility there, downward flexibility, and then towards this direction the flexibility. And what it means, you are having a more tolerance. Suppose a compound is having a 5 micron, you will have no problem. Suppose we are having, we have got a lot of problem making a 5 micron. If you are giving a 0.1 tolerance, then you will have a more flexibility in making them. So that way the machine is capable of making the PQ square is helping to make the machine, making the process window for that particular machine. That is the main advantage of that. What we call it, suppose you select a center line, center point of that, draw a line from that, this is called a die line. So for this line, we can calculate and bring from the PQ square diagram, these are all the values will come. What are all the values selected? These are all not much, but one more thing, I will come to the metal pressure. Already I told you. Gate velocity, we can right click it. Gate area, we can come. Phase 2 velocity. This is where we are having a difference. Phase 2 velocity is nothing but a plunger velocity. There in conventional, we could not able to find out what is the plunger velocity. Here gate area is already, for this gate area, suppose 4.51 meter per. Suppose the machine is, it is only some sample is given, probably this seems to be very high, which is not, for this machine we have calculated, we have not calculated, we have taken a random and then checked up. Normally, if we are putting a right value, this will become 2.5 to 3 meter per second. Cavity fill time is will come. So now we will come to the metal pressure. What is the metal pressure? What exactly it is happening here? This is not related to the specific injection pressure, which is created by the multiplier. This cavity pressure, suppose we are inserting the material inside the cavity, we are trying to send the material inside through the gate. Here, the energy is converted, this energy is coming to a kinetic energy and then pressurizing here at the gate. This will be converted to two-way. One is the kinetic and it is a pressure energy. Because of this velocity, the energy created inside, the pressure energy created inside the cavity is called cavity pressure. Once the cavity is filled, that only the multiplier will come into picture, that will get more skews inside the cavity. Okay. One more thing, what are all the variables that we can do that? Suppose if I want to make a higher velocity, since I am having only 2.5 or 2 mm wall thickness, then you can select a point which is having a more velocity. Means what will happen? We want to reduce the gate area. Gate area to be reduced, and as well as the flow rate has to come down, but pressure will get up. So this calculation, how to understand all these things. Suppose if I am giving one more thing, I will give the variables. What are all the variables which we can handle in the PQ square diagram? Now you can see there's a small plunger. Always will have a machine. Will have a 3 plungers, probably mid plunger and then small plunger and a big plunger. Probably we'll take 2 cylinders. How the PQ square diagram is getting varied? Suppose the small plunger, larger plunger. Small plunger is having a. This is going to be a small plunger because it is having a less discharge, more pressure. That is why. Here, if you are going for a big plunger, lesser pressure, more water. Now we will go back there. What you are doing it there, I am going to make a line. Suppose this is a plunger, what I am going to have a mid plunger. Now I want to make a big plunger, means the pressure will get reduced, your window will get changed like that. The window will come little less. It will be crossing like that. Okay, understanding this line is a plunger line almost. Suppose we are changing the plunger diameter, this line will get changed. If you are going for a smaller plunger, this line will go up. Pressure will go up. If you are going for a big plunger, the pressure will get down. But at the same time, if you are going a plunger, the key will get reduced. If you are going for a more size, the key will get increased. And one more thing, suppose if you could be able to change the pressure in the machine. Normally we used to work with the 150 bar. Suppose I don't want to, my machine is getting down, but probably 125 is only creating. What will happen at that time? Same thing, lines are coming. So when the pressure is going to down, your Q will be more, Q will be less, pressure will be more. So this concept is also going to be applied. Suppose these are all very, very, very rare used items. Changing the machine power line, normally machine pressure. This higher hydraulic pressure, this is a lower hydraulic pressure. These two curves will get changed. I told you one small thing. I told you. What is the altered machine power? Is nothing but a HP conversion. What I am saying that suppose if I go for a 25 HP for a 250 ton, I want to go for a lower of HP, about 20 HP to save the power. Your drawing line will be different. This is what you would have to understand. Here, in the machine, we want to change the 125 to 100 or 125 to 150. This will be the line. The parallel line will come into it. It will get changed according to more pressure will go up, less pressure will come down. Now, this is another understanding of this. The smaller gate area will be always here, and this is a medium line die line. Suppose we want to make a smaller area, it will go up. What it means, if you are going with a smaller gate area, your pressure will get up. Why I am telling that? For a pressure tight components, always select a smaller gate area to get the advantage of the cavity metal pressure. For a larger gate, the decorative component or engine component, we can select a larger gate area. We'll have a lesser problem in the time. So these two things also we'll have to understand and then work on them. So as I told the PQ square diagram, this is a gate area selection from die line, and then this is a gate speed general. It is only giving some what are all the lines it is top. Gate area selection from die line, cavity metal pressure due to velocity energy. These two things are made in that. So as I told, this is a fill time line, this is a gate area line, this is a gate speed line. What we did in the PQ square diagram. With this, I want to stop. And then any clarifications required in this case from the audience? I'm requesting you to any clarifications required.
Anyone who wants to ask a question, please unmute yourself and proceed with questions. I think Tirunyanam sir has a question.
Yeah,
Sir Tirunyanam sir, if you can unmute and ask, you can proceed, sir.
Am I audible?
Yes, sir, you are audible.
I have a fundamental thing to ask. Not simply, the Bernoulli's equation is valid for liquid flow, but the filling.
Yeah, that's what I told you. No,
Yeah.
the CD is a real value. Suppose if it is liquid, it will be 0.8, 0.9 and all that. If you're going to slurry, it will come down to 0.5. So we treat it as a slurry there crossing the gate. I already told you earlier, it is not a liquid, or aluminum itself is not liquid, high density. So normally water is 1, or fluid is, even hydraulic oil are also within 1, 1.5, 1.2. But as per the density of the aluminum is considered for 2.7 means it will become 2.5, 2.3 as a liquid aluminum. The density is of more, and as well as the slurry is formed near the gate. So all these things make the CD value will get down. That is why NATCA has already given, that is a 0.5 is the standard value for aluminum discharge efficiency near the gate. Probably now the simulations have started coming to find out the CD value. That flow 3D is already given that. We are also working that. That will be given after 3 or 4 months. I will give a paper according to how we can calculate CD value from the simulations.
Thank you.
And one more thing I told, probably I said, sir, how when I told you that there is a lot of calculations are there. How we can make a PQ sky diagram for our machines? This is a big question. Actually, now that is what I am saying. The NATCA is already having a software which you can directly buy from the NATCA for this PQ square diagram. You can put your machine value, and according to that, our plunger diameter and all that, according to that, it will vary and give you the gate area. This is the one way. And the second time, we are already making the same software, and then we have started using for the past 10 to 15 years. That will also, I am trying to bring it to commercial within a month or next 1 or 2 months, a separate module for PQ square diagram. So you can keep touch with the Dietech so that we will try to release, and then probably it will go to through Alucas also. I am thinking to, just like a NACA, whether we can use Alucas also to release this PQ square diagram for the benefit of people. But little commercial will be there. That will come into picture for after 1 or 2 months. Any other questions?
Yes, sir. This is Sandeep, sir. So,
Yeah, please.
yes, sir. So this is regarding the dry shot speed. So when you procure a new machine, so the dry shot speed can be achieved whatever given in the manual, but over a period of time, maybe 2 or 3 years or 5 years. So in a diecast, normally we use the old machines regularly. So whether this calculation helps in deriving the dry shot speed, or we have to take the actuals.
That is one thing. What I am telling the two thinking is that is one is a dry spot speed for a new machine. What the machine supplier is giving, that is also applied for a short sleeve conditions and plunger clearance. That is also going to be taken into account. Please understand. So what I am saying that suppose if the plunger and as well as short sleeve conditions are very poor, your dry shot speed will get reduced. That is one thinking. Now, as per that, another thing, what I am saying that if you, as long as you are keeping the pressure of 150 bar, probably hydraulic cylinder will never change anything on that. That friction or something, it will be very, very low. Probably little seepage will be there. That will be negligible. But normally, the dry shot speed will be getting affected because of the plunger and as well as the short sleeve conditions. If you could be able to maintain that for any old machine or new machine, If we could able to maintain that, as well the pressure if we could able to maintain, and as well as the plunger and the soft sleeve conditions if we are able to maintain, probably whatever the value is declared by the machine, it will through. Probably by 90-95% it will come all right. If the conditions of the alignment between the injection center or the condition of the source sleeve or kind of clearance of the source plunger tip, these are all going to matter. Suppose we want to make that, try to load the die and then put your plunger and then put your sleeve. Try to find out a plastic transfer. Probably Neptec is having that unit. If I am not wrong, in Chennai, they already developed a unit to find out this PQ's guide, that is the velocity, dry shot velocity can be calculated from that velocity transducer. Probably you can contact Neptec also to evaluate the existing machine, what will be the dry shot velocity. We can measure and we can take that value.
Okay, thank you.
Any other thing? Okay, think there's only additional what I told. I have already told that is a solid fraction. I'm giving 2 or 3 slides on this. What is happening? This is a continuous jet. This is a coarse particle flow, and this is atomized flow. We are always trying to come out with this. So we are trying to make after the gate. It's a coarse particle flow, nothing but a slurry. It is going to come as a slurry. In this slurry, there will be a percentage of solid, percentage of liquid. Certain times, probably even people will be succeeded by making an atomized flow by reducing the very, I mean, almost it is we are throwing all the material as a powder. So if the powder started coming in the die surface will be, you can able to see clearly the material aluminum will get stick very, very strongly, and then the soldering effect will be very high. So these are all going to happen in case of an atomized flow, but the porosity will be less. Even I have been experienced. One die caster, I made the die, but they made it as an atomized way. That is making 5 meters per second. They started, this is a vibrating mounting, engine mounting bracket. They started giving a more 5 to 6 meters per second, whatever the machine speed is there, they started using it. But die lab has gone very bad, but according to that, they could be able to produce a component with a little soldering and all that, but the nil porosity. This is characterized coming probably in atomized flow. All the air will be get away from this because of the small, and then there will be no turbulence, high speed, all the air get out of that. So sometimes people started using with it. Sometimes you know that the defect is also going to be useful. So this defect of phenomena can be used for making a nil porosity casting. Sometimes what I am saying that, but it is not recommended. But this is a one technique which is already available. Now we are talking about the coarse particle flow, having some solid fraction and a liquid fraction. How to find out this type, or whether it is going there or we are going there or we are going, how to find out? Some Reynolds number calculations is that this flow, they are given the flow can be coarse particle flow or solid jet flow as seen in the figure. If it is in 750, they have given some 750. How to calculate that figure 750? They have given some calculation. This is predominantly NATCA. Probably jet is automation value, and the depth of gate is the density of molten metal, gate velocity, all this put into the picture. Then we will get the J value. From the J value, you can able to what it is happening inside the die. Before making the die, what would happen? We can able to judge. Probably this is also having a lot of calculations. Probably I am only picking up from the NATCA and then presenting you more the concept. I do not know the exactly. We are also not calculating this type of calculation and all that. But we are trying to find out what is the solid fraction and then what is the liquid. This we are trying to find out from the flow theory, which recently they have introduced it. Please try for that. Try to find out the CD. CD value is going to be the breakthrough. Breakthrough. Why I am telling the breakthrough? Then only whatever your calculation will start working the die. There is a gap is there. The CD is only going to affect more and more, because we are talking about 1 and 0.5, whether it is a 0.7 or 0.4 or 0.3. 0.3 means 30% or 50%. What really going to happen? That much efficiency is very bad actually, 50%. But India aluminum it is happening. So we want to find out. So what will be the solid and the liquid? Probably the CD value can be able to fix. From there, the calculation of PQ square will be more and more value for the practical purposes. Thank you then. Any other questions, please? From the audience? நான் நல்லா பண்ணிருக்கேனா or otherwise புரியல
இல்ல sir. I think it was really good. Anyone else, please feel free to open up and ask questions.
கொஞ்சம் questions எதுவா இருந்தாலும் well understanding please ask so that at least to understand concept. I'm not talking about calculation or something like that. Just the concept whether you got it. That is what the main idea behind it.
I think Tirunyanam sir.
This paper is only to make you to feel the concept.
Sir, unmute yourself, sir.
Am I audible?
Yeah.
Yes, sir.
I mean, is it
Sir, you are audible, sir.
Is it necessary to take the speaker square diagram for machine every year?
Yeah, every year what it means, what I am saying that's why I told you, hydraulic line normally you do not have a problem unless you are able to maintain the pressure and then measuring the pressure on the plunger, that plunger area. So if it is going to be pump pressure, is going to be a plunger area, if you are able to measure, then this will not get changed. It is only a rubber item which is going to be slide in the board. Actually, the problem is on the alignment of the injection between the short sleeve and the plunger rod, and as well as the condition of the short sleeve and the plunger clearance. These three has to be maintained, and every month even you can able to see the alignment. Nowadays it is available, even the calligraph are available to see that short sleeve versus injection position alignment. Some machines are having adjustable. There we will have to be very, very careful. If the machine is fixed by Toshiba and all that, they don't have even the variable injection position. There we need not worry much about that. But in case of HMT and other machines, they have got a 2 or 3 injection position. That is the problem for you. So probably you will have to see that plunger alignment with the short sleeve and the condition of short sleeve and the plunger. Then the dry shot velocity, what you are planning, it will come to you. So every year, if it is done, it's good. I'm not saying it is not bad. Probably what I told, the injection position is getting very low. That will be very dangerous. Suppose we are changing 100, 150, then bringing down to 100. So probably that alignment between short sleeve and injection center to be rechecked.
Thank you.
Thank you, sir. Thanks for your time, and then thanks for the opportunity given by the IIF to present this paper. Thanks for Sendil and Siddharth and Ramanan, Shaktivel. Thank you, sir. Thanks a lot.
Sir, there are some more questions. Somebody has raised their hand.
Please.
Yeah, NVPD, Sandeep Rutala. You can please unmute yourself and ask, sir.
Yes, sir. While calculating this tonnage, while you are selecting the machine tonnage, so I also seen some of the calculations with the sliding course, so with a wedge angle. So why that is not this one?
I've already told.
Yes. So it is why there is a difference of this 21 degree and 5 degree for mechanical and hydraulic.
The component what you are applying, no, in the side core you are applying the pressure, but locking in the opposite direction. Okay. Now that plate against that is that axis, we are applying the core pressure in the opposite direction. That's a 90 degree.
Okay.
So for that, what we are doing, we are stopping with either one wedge. That wedge on the angle is getting varied. Mechanical core is 21 degree or 22 degrees, some 18 to 21, and hydraulic core 3 to 5 degree. So according to that element will be directed. Only opening the die will be this percentage, the tan 5 and tan 21. All other will be taken care of. The die will be taken care of. The wedge thickness will be taken care of. The force trying to open the die is only this much. All other will be taken by the die loading. That is, the die material is taking care of that force.
So you mean to say the mechanical core it should have the 21 degree of angle?
18 to 21 is a normal.
Okay. 18
to 21. Why I am there is a mechanical core action on the. If you are going for below 18, you will get stuck on mechanical core finger cam will come. Because why we are selected 45 to 21 means the force what you are acting on the cam should be optimum in case of a 18 to 21 degree. Suppose we are going to increase or reduce, the finger cam action will be, the force will be more on the finger cam. That is the optimum force what you can have the 21. Here tan phi, why you are selecting the tan phi is only what we want. We want only a 90-degree lock. Probably we want to release the core from the die. That is why we are giving some degree of for 3 to 5 degree. If you are going to lock it at 0 degree, what will happen? Your die locking force will never get increased. It will be taken care of the die material or housing. It will be taken. But fortunately, the function requires some draft to release the core. That is why we are given 3 to 5 degree there in hydraulic.
Okay.
Could you able to understand what I am saying?
Yes, sir.
Sir, there is one Mr. Surya Narayanan who has raised his hand. Sir, you can.
He is my boss, sir. He is my boss. Tell me, Surya Narayan. I think I want to hear his voice.
Good evening, Prabha.
Good evening. Tell me. Fine.
It was nice. I have one question, the same slide what you are presenting.
Yeah.
The same slide, same slide.
This slide.
I fully the same slide. The 21 degree, 80 to 22 degree is the sliding angle. I fully agree with you. I have one confrontation. I don't know whether I'm right to talk on this forum or not, but you know me. So I'm talking on this. Tan 5, that 5 degree, it is falling well within the self-locking taper. Morse taper is called 1 to 7 degree. It's a self-locking taper. Don't you think that it will have more force for the die to open when that is get locked with this taper?
Still, what I am saying that.
This is the same mistake.
I put this here, Surya Narayan. What I am saying that I don't want core force to be transmitted to the locking force. This is my idea. Okay. So what I am saying that if I am going to make the concept, what I am saying that if I am making a 90-degree lock, then this force will be transmitted to the housing. Okay. Fortunately, what is happened now? This wedge is coming and engaging here. It can be a 3 degree or 5 degree, one to only engage and release. Okay. Now, what you are talking about the taper locking of the self-locking, no? You are talking about the self-locking.
Yeah.
Self-locking will be in a 3D dimension. It is in one plane. So it is not at all coming into picture at all. It is only in one plane.
No, I'm not connecting this to the PQ at all. I'm connecting.
I am not connecting this. I am not connecting to the PQ. I am not connecting to the PQ diagram. I already told. It is only referring the calculation machine selection. That's all. PQ diagram will never come into picture at all. Please understand, this area is something different. So from that, right at the beginning itself, this is only reference for machine selection. From the machine selection, you should know what is the machine to use for the PQ diagram. So that question will come. That is why I told the machine selection. I have not told the tonnage selection. I told only machine selection.
Okay.
So PQ diagram will never deal with the only to select the machine what we need. That is why we are giving that. I have already told this narration also.
Okay. Thanks a lot.
Thanks, sir. Thanks a lot.
Thanks a lot.
Any other question, Ramana?
Any other questions?
Just one more question. Same slide. What you are about the wedge tan 5 degree. Can you hear me, sir?
Yeah, please tell me, sir.
Yes. In site work, even though we are using hydraulic cylinder, we are using the wedge angle of 8 to 10 degree. Right?
10 degree.
8 to 10 degree, 8 degree, 10 degree, 12 degree. Various suppliers are using various.
It is not question about what I am saying that I told you, no, that is you can have a better tonnage of the machine of that component. You can use a 10 to, what is it? I can put it in that. What I am saying that if you are using a 5 degree or a 10 degree, the releasing will be more convenient in 10 degree. But at the same time, you are going to transfer some force along the wedge locking, die locking, tonnage locking, whatever the die parting against that, you will be transferring some force. In case of 5 degree, it will be less, 10 degree will be more. But advantage of 10 degree is the releasing is very easy. 5 degree is having some friction. Would you able to understand what I am saying?
Yes, sir.
It is not wrong using a 10 degree or 10 degree or 5 degree.
Case of using 10 degree, here the tan 10 degree will come. Is it right?
10 degree will come, nothing else. 0 degree will come.
This is what.
So when we are putting a 10 degree, your value of projected area on the core will be becoming more. So in turn, the tonnage will get raised.
Requirement tonnage will be more. Yes, I agree. Okay.
So that is what. So we are compromising by way of tonnage. If you are reducing the angle by 5 degree, even some people are using the 3 degree to get the advantage of tonnage. But the friction will be more. That's the main. Probably that wedge has to be nitrated or something like some other treatment should be grounded and then nitrated. These are all the requirements are there for a 3 degree. 5 degree will be normally a milled surface with a little grinding is okay. If you go with 10 degree, probably milled surface directly it will start work by polishing and all.
Yeah, okay. Thank you.
Any further questions?
Yeah. One more question from me, Sandeep sir.
Yeah.
So while considering this PQ square, so it's a purely theoretical. So how far can we say for a given die we can achieve if the process point is within the operating window at the middle of the window? So how far we can say it's a stable design or a very good design?
I will come back. So still they are having a doubt. Actually, the PQ square diagram is not telling only the value, but the input is given from you, from the machine. If you could be able to maintain the dry site velocity, what you are giving, you could be able to measure and then give the value to the graph. Number one. Number two, consistency of maintaining the pump pressure. Number two. Number three, what I am saying, the gate area is going to be given only it is going to be calculated from the PQ diagram. So dry shaft velocity, normally what the problem, what we are facing it only, the velocity what you are deciding is not coming. Suppose if I am saying that a particular die is designed for this gate area, but probably it may fall here also. It may fall here also or fall here also or something like that, even it will go here out. What exactly happening? Suppose the point it goes out, what it happens? What is the meaning of this graph? Whatever the value what you are giving is machine performance line. Suppose your point is coming here, what it means the machine performance line, your performance machine is not equal to this line. So the real problem today is only the CD value what you are assuming. All others are true values which you are only giving them. Suppose you want a 40 meter per second, so if you want a 50 meter second, you can put the 50 meter second line. If you want only 25 or 30 meter second, you can put the 30 meter line. You are only describing the PQ square diagram. And this is warranted the vertical line what I am showing that, no, I told you the vertical line, it is coming from the component. You are not deciding it. It is coming from the component. What is the weight of the component, or after the gate, what is the weight of the component and the volume? Based on that, we are finding out the maximum fill time. So this is decided by the component, and this is decided where we are facing a problem only a machine performance line. If you could be able to find out a right, or otherwise if you are making more and more accurate of practical values is equal to fitting value in the graph, then you will get that line. Apart from the what today is a gap is at the CD value. That CD value we are assuming is average is a 0.5 for the metal of aluminum which is transferred towards the gate. So now the flow simulations have started coming. Please try to use the flow simulation, try to find out the particular gate what is the CD value, fit it to the graph, find out this gate velocity, you will be benefited. Probably there is a practice, but what I am saying here, going blindly, suppose my point is, if I am selecting a point here, my error even if it is there, it will go little here and a little here or a little here or a little here. The practical will come here. Suppose if I am going to blindly and then putting a point here, the component will get rejected since it is not coming inside the performance line. Component will fill with a lot of defects. Suppose we are going below down, that's another problem. So try to fit the curve and then try to find a center, put the value of gate area according to this, then your error, whatever you are making the error, will be substituted with this process window. This is what the idea behind it.
Yeah, exactly. This is what my question is. So if you go about the out of the process window, does it will give impact to the casting? Definitely.
Yeah, casting, lot of casting.
Or is there any cases that even out of window also castings produced with a good quality?
Definitely, that's probably what that is a gap is there. I'm not saying still that gap is there. Try to find out the CD value from the simulation, put it in the graph, and then also try to find out the real value from the machine. Probably, definitely it has to work.
Okay.
Yeah, none of the constant is there. Only the CD value is a major problem.
Okay.
Any other questions, please?
Okay, assuming that we are done with the questions, I would like to remind the members in the session that this is being recorded. So if you have any clarifications for this regarding the session, it's always available on our YouTube channel, IIF Chennai. Sir, Prabakaran sir, it is.
Yeah, please, sir.
Sir, we thank you wholeheartedly because we know how busy you are, how efficiently you run all your companies and organizations. So thank you for sparing time. And I should personally thank him because I only asked him twice and he was readily willing to come and present it to the audience just to share knowledge. So on that aspect, I would thank him again. And I would like to thank IIF Chennai chapter for having this webinar session for non-ferrous topics so that it helps to grow the non-ferrous industry as well, seeing the future projections. So thank you again, sir. Thank you, IIF Chennai chapter.
Thank you all. Thank you. Thank you. Thank you all.
Some people were asking regarding the data for this presentation. Rather than sharing the file, I would say this is being recorded, so you can see it on the YouTube channel. I think that is better. Because
we can share that presentation with that. As for the, the speaker doesn't have any objection in sharing this presentation.
Sir. Yes, sir.
Thank you.
Okay, let them have the benefit of it. Even if they want, let them send a mail so that we will try to reply for that also.
Very nice of you, sir. Thank you.
Sir, one person.
I'll send the presentation to IIF so that you can share whoever with them. So IIF, I'll send the presentation today, sir, so that you can directly share.
Okay, great, sir.
Sir, Prabakaran sir, one personal request, sir. We very well know how technically sound your son is also, Mr. Arun Vinay. But unfortunately, we couldn't get a session in Aluminum Conclave. But if we can be, spare some time, just like how you did in the future webinars, whenever he has time, it will also be useful for us.
Yeah, definitely. I'll try to interact Arun. He is little busy with that education and all that. I will try, but probably he is trying to complete it. So probably you will be another project to get free.
Thank you, sir. Thank you all.
Thank you.
Thank you, sir.
Thank you all, sir.
Thank you.